Yeah, so, hello everyone. Uh, do you have any questions about last lectures, about the problems? Mm. Okay, so then let us start. So today I'm going to tell about Laplace equation in 2 dimensions. Maybe maybe Poisson equation. It's correct name. Uh, so. Hmm? Let us let us see. So I want to tell about this. Also about separation of variables in spherical coordinates, and I also wanted to tell something about nonlinear equations at the end, of course. But uh, Mm, before this, there should be some special functions, not so many of them. Uh, and now, of course, about this equation, about conformal maps, which can be used for different domains and so on. So. Um, and also about the heat equation on a circle and about elliptic functions. So, why did you ask? Yeah. Yeah. Ah. Mm-hmm. Ah. Mm-hmm. Uh, okay. Okay. Uh, uh, do I remember what is the gain function of this equation in R2? So, namely, if you have R2 and we have an equation like Laplacian of u equals to f. How to write a solution for u in terms of f? Like, so it is some d2 x prime g of x, so it's u of x equals u of g of x x prime f of x prime. Who remembers the expression for this gain function? Yes. Yes. So the coefficient is a minus 1 over 2 pi. If I remember correctly. Yeah, like this. Mm, so it's correct. Oh, it should be. It should be correct. So how to remember the sign? We can just draw this gain function for d equals to 3. In this case, this gain function is decaying. It is 1 over r. And in this case, on this sign should be the same. So it should go like this, but in this case, it is minus logarithm of r. In principle, divided by some constant. Because it does not go to zero at infinity, so we cannot define the Lagrange function uniquely. And concerning this coefficient, it is the length of a circle, because we should have an equation like integral over integral around zero. Dn times gradient of g should equal to 1. And it is what can be obtained from so it is what we get when we take a gradient of this function. So is it let me think. Let me think if the sign is correct. Oh, sorry, the sign is wrong. It was actually so with this minus sign I wrote a green function for minus Laplacian, because its derivative in r should be positive. We should have a picture like this. So it is 0, and and gradient of g should point from 0. In this case, this integral will be positive. So this is actually a picture for minus g, and here also for minus g. Sorry. Yeah. So it is this grand function, so we can write such solution. But now let us try to study another case. Let us study this equation, for example, in a disk. So let us say that
What is the integral
around S1 with some small radius epsilon. Actually, no, any epsilon. Oh, so we take a circle of radius r around 0, and say that it equals to the integral over dr dv ds Laplacian of g. It equals to this, right? So this equals to 1 by definition, because can function solve the equation with delta function in the right hand side, and this one equals to 2 pi times r times gradient of g. So this integral equals to pi r absolute value of gradient of g, or maybe better to write like n and gradient of g. And is the unit vector pointing from 0. And we see that actually this equals to this. So, but now let us study the following problem. Let us choose some domain D such that D is so it's interior of the unit circle. X squared plus y squared is less than 1. And say that we have a Laplace equation with some, well, we can study different variations of this problem. Let us first study the following problem. So, Laplacian of g inside d equals to some function f for x in d. And also the boundary condition. Equals to some not of g of u. U of x equals to u0 of x for x belonging to boundary of this domain. And let us start from the homogeneous problem with f equals to 0. So first, let us study the case f equals to 0. So to solve this, we can actually use the same trick as for the wave equation. And namely, let us introduce new variables. Z equals x plus I y, and z bar equals to x x minus I y. So now the question, who are dz and dz bar in terms of dx and dy? So, who knows what it is? Dx minus I dy. Well, yes, so that dz of z equals to 1. Yes, and dz bar, we can just conjugate it. dx plus I dy. And so if now compute dz bar, we find that it is 1/4 1/4 of dx squared plus dy squared. So it is 1/4 of Laplacian. So if you now want to solve Laplacian of u equals to 0, it is equivalent to say that dz bar u equals to 0. Or, also, there is a kind of shorthand notation for these derivatives. dz is called by d, d that oh, d z bar is called by d bar. So we have this equality, and as for the wave equation, we can now say that dz bar of that function, so it follows from here that dz bar of dz of u equals to 0. So dz of u is holomorphic in this disk. And also, we can look at this in the opposite way and conclude that dz bar of u is also is anti-holomorphic in D. And who knows the general formula for a function which is holomorphic in a disk? So here we have 0. Hmm? So, no, maybe it's too fast. Of course, we can do this, but now at this moment I'm asking just about the Taylor series. Yes. So if it is holomorphic in this disk, then we can conclude that dz u.
What you mean when you say anti-holomorphic?
It is well, it's by definition a function which is queued by z bar, which is just sorry. No, it's fine. It is a function which is queued by d. So homomorphic functions are those uh, d bar f equals to 0, anti-homomorphic. Like you can rewrite this in terms of imaginary and a real part of f, and it is called Sherman conditions, probably. Right? So it is a pair of equations on imaginary and real part of f, but maybe it's more convenient to write it this way. So does it answer the question? So, okay, so if this desert of u is homomorphic, we can write it as a series. Uh, some oh, let me think. Mm, so I will write it from the very beginning in such form: Cn and Cn Zn minus 1. Mm. So it is such serious for arbitrary. So there should be some condition on this coefficients Cn, so that is so that it is really homomorphic in this disk. And who can tell what is the condition for this coefficients? Uh, Uh, yes. So absolute value of so uh, mm, how to write this, that um, Cn at n goes to infinity are all of 1. So Cn's are all of 1 when n goes to infinity. And now about this part of our function. So dz bar of u is anti-homomorphic, and so we can write that dz bar of u is sum from n equals to 1 to infinity. Let us call it n c minus n z bar to n minus 1. And having these two expressions, it is now obvious how to write the general formula for u. So we find that u equals to C0 plus sum from 1 to infinity Cn Zn plus sum from 1 to infinity C minus n z bar to power n. So there is some constant which disappears after the differentiation. So u of z bar, and here we can just say that it should go. It should behave like O of 1 at both infinities, plus and minus infinity. So maybe mm, it's not necessary to ask that it is O of 1. It is enough to ask that Cn over C n minus 1 So it should be less or equal than 1 when n goes to infinity. Maybe better to write that it is 1 plus small o of n. Yeah. Uh, well, something like this. But we actually don't need this condition. So now we have this expression, and only one thing which we need to do is to compare it with the boundary value of u. You now see that if we choose z equals to e to the I phi, and correspondingly z bar equals to e minus I phi. This corresponds to point on the boundary of our disk. So in this case, we will have that u0 of e to the I phi equals to the sum. Well, let us just write this as a sum of all integer numbers, Cn e to the I n phi. And that's it. So we just see that these coefficients are Fourier coefficients of boundary value of our function. So and if you want to write a solution, well, we can say that just read the coefficients from this formula. But we can also write that this coefficients are equal to the integral of u0 of e to I n phi from 0 to 2 pi or I phi e to minus I n phi d phi over 2 pi. And if you substitute it to the formula for u, and then we get this expression that mm, u of z bar equals to or maybe it's better to write it as here we have a 1 which will compute S0 plus sum from n equals to 1 to infinity Cn e to I n phi plus sum, oh no, what would be right? It should be z to the power n, the n phi, z bar to power n, e to minus I n phi. No, it's not correct. It should be minus I n phi, and here it's plus. U0 of phi. And now we can compute these two sums and get what is 1 plus z e to minus I phi over 1 minus z e to minus I phi. And here it is z bar e to I phi 1 minus z bar e to the I phi 0 of phi. And we can also rewrite it as let me think. Oh, maybe we can just get all the terms together, and this will be 1 plus root value of the squared minus so then in the numerator we definitely have 1 and so this one should be correct, I think. Yeah, so there are 4 terms here, to here, and to here, and the remaining is in this one. Thank you, yes. 0 of phi of e to the I phi.
Also, I didn't check didn't check correctly, but shouldn't we have in the denominator, the last one of the two I5
Yes, yes, it is correct. So this one, yeah, the z bar. If we introduce polar coordinates also for z, so if we say that, so we can write this formula for like u0 of some r e to the I theta. And then well, it is the value of z. Z equals to this one. It will equal to the integral from 0 to pi. Oh, sorry, u of r equals d phi over 2 pi 1 minus r squared u 0 of e to I phi over 1 plus r squared minus 2r cosine of theta minus phi. So, and there is such a kind of formula, and we can also check independently that this expression turns into the delta function when r goes to 1, because this goes to 0. So if you say that now r equals to 1 plus epsilon, then this formula u of r e to the theta becomes integral from 0 to 2 pi d phi over 2 pi minus thank you. So it will equal to epsilon to 0 of e to the I phi, and here on this denominator, so we can expand this cosine around theta equals to phi, because otherwise it is 0 anyway. So it equals to no, let us first write it as 1 minus r r squared plus 2r 1 minus cosine of theta minus phi, and so it is 2 epsilon is 0 of e to the I phi, and here it is epsilon squared plus plus theta minus phi squared. And we can recognize here the epsilon sequence which converges to the delta function. So as a consequence of this, we check actually u of r e to the I theta goes to u0 of e to the I theta when r goes to 1. uh, so it is, we can write that it is integral from 0 to 2 pi delta epsilon of theta minus phi u0 of e to the I phi d phi. So is it okay? So right. So in this way, we know how to solve a boundary value problem for this Poisson equation A in the disk. And are there any questions about this? So now let us let us switch to another problem. When boundary value is 0, and we know to find the solution of an inhomogeneous equation. So, namely, we want to find a Green function in this disk. So, so 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 namely, we need to solve the following equation. Laplacian of g equals to delta function of of x, delta function of x minus x0, and g of x x0 x0 and g of x x0 equals to 0 when x0 when x is on the boundary. So I have the problem which we need to solve, right? First, let us solve some simpler problem. Namely, let us put x0 equals to 0. Hmm?
Just working on the last integral, the term 2r1 minus cosine of theta minus phi. R is 1 minus epsilon. Where is the first term?
So, do you want to write here 1 plus epsilon? 1 minus epsilon. So we can divide this epsilon by this factor. So it's just summary scaling of epsilon. So yes. So we can rewrite it like no. So it's more or less clear that we can write 1 minus epsilon here. Then this, then instead of this epsilon, we can write epsilon over square root of 1 minus epsilon squared. And we can also put it here. So, oh, let me maybe write it explicitly. So, and here it is epsilon over square root of 1 minus epsilon. And here we see that it's actually to epsilon, that it is this epsilon sequence for the delta function, and it differs by something of order 1. So,
yeah. What we're checking there is that the solution we found is a sort of continuous with its boundary condition, and so
no,
like that part there, we see that for r that goes to 1, the solution we found is coherent with the boundary condition.
yes, we are just checking that we did not make any mistake. Yeah. So, and checking how it works technically. That this expression is actually is actually a solution of this boundary value problem. So. Um, So in principle, we can also check that Laplacian of this expression is 0 inside this disk, and maybe it's not so trivial computation. But we know that we constructed this expression as something which is cured by Laplacian, because it's sum of homomorphic and anti-homomorphic functions. Right? You just have just written it. Have just written them in some different form. Mm. Uh, Okay, let us now solve this equation for the green function when x0 equals to 0. And who can tell such a solution using the formulas that we already know?
The usual green function with the addition of the supermode constant such that it vanishes on the boundary.
Yes, so we can just take this formula and put the L equals to 1. So, so this gain function of x and 0 equals to 1 over 2 pi logarithm of absolute value of x. Thanks. So it can also be written as 1 over 1 over 4 pi logarithm of z plus logarithm of z bar. No, it's a bit dangerous because this logarithms are multi-valued, and we can in principle choose these constants in different way. So it's safer to say that it is a logarithm of z bar. So now what shall we do if we want to find this gain function for arbitrary x0? I propose to use conformal transformations, and namely, let us say that our because absolute value of x is x squared plus y squared, or a square root of x squared y squared. So it is square root of z bar. And I removed square root by because we want it to be 0 when absolute value of z equals to 1. So, and by the way, looking at this formula, actually looking at that formula, we can check some we can check some properties of generalized functions. So, this is some remark. So we know that a Laplacian of 1 over 4 pi log zz bar equals to a delta function of 0. Delta function of oh, it's a good question. How to write this? Maybe let us write it as delta function of x. And if we now substitute this Laplacian as for dd bar, then we see that it is 1 over. Then we see that it means that dd bar logarithm of zz bar equals to pi delta of x. And if we now compute the bar derivative of this logarithm, it will kill z, logarithm of z, and will keep the bar of logarithm z bar. And it will give us that d of 1 over z bar. Or maybe, no, maybe I would like to write it this way. Let us write it like this. The bar of 1 over z equals to pi delta function of x. So we can find such relation. So, and we can also understand this in terms of in terms of residues, because maybe. So think about this. No, maybe it's enough. If we need this later, we can think about this more. So, so there is such a relation for generalized functions. So, well, in particular, it says that if a function has a pole at some point, that naively it seems to be homomorphic in this sense, because it does not depend on z bar, but it is it is actually not homomorphic up to some generalized functions of delta function, probably derivatives of delta function, if we add here some power of z. So okay, so now this remark. Yeah, now concerning this green function. So Suppose that we solve this equation. Uh, Suppose that we found some green function, and now we try to substitute here some. We want to make this z a function of some other complex variable. Mm. Uh, mm, mm. Oh, wait, let me think about the notation. So now let us choose some function uh, w of z, some homomorphic function. Mm. So so the bar of w equals to 0, and then consider g w of z and z bar, which is equal to 1 over 4 pi logarithm of w of z and w of z bar. And compute a Laplacian of this function. So, namely, uh, so Laplacian of this GW of z and z bar equals to 4 d2 over dz dz bar. Logarithm of w of z w of z bar. And now let us write this Laplacian as derivatives in w. Like it will equal to 4 dw over dz d over dw. Mm. W bar over d bar z bar d over dz bar. D over the W bar. Acting on this 1 over 4 pi. So it equals to, here we have this, so here we see just usual Jacobian in W variable. So it gives us that it equals to dw over z, so value squared, times delta function of w of z, right? We can actually think about multi-dimensional delta functions and understand that it will equal to so that if we try to express it as a green function of z minus z something, then it will cancel this prefactor. So we can write that it is delta function of what so it equals to oh, so this 4 should be removed. So it equals to delta function of this two-dimensional delta function of z minus z z star of w, where this is a solution of the equation that w, oh maybe let us write the star. And the star is a solution of the equation w of the star equals to 0. So the idea is that we perform some conformal transformation and act with this conformal transformation on the green function. So we check that it is still a green function, but with a singularity at some other point, right?
In the turbulent for the last line, after the first equal, should be 1 over 4 pi.
Yes, thank you. And now let us try to do this for our case. So we want conformal transformations which map this disk to itself. It's a transformation given by some function which is holomorphic. This. So now we want to find such functions which map our disk to itself. So here is coordinate z. Here we acted with this function w. So it is our d. And we should obtain our disk. So the question is, what are the functions actually, well, it is easy to write a function which trains with disks, but we also ask them to be invertible. So there are functions which, uh, or maybe we can discuss. Um, Let us discuss it right now. So it's actually a, a bit simpler side question. So suppose that we have complex plane, and we are looking for functions from C to C. And the question is, what are the invertible holomorphic functions from C to C? Well, holomorphic, it's too much. Mm, no. Let us add here infinity. And since we have infinity as a point here and there, here we can ask for meromorphic functions. This is also denoted by C hat. So the third question, how can we write an arbitrary meromorphic function? Mm-hmm. Yes. So so it is some polynomial, like if mm, mm, or maybe let us say it from the very beginning. So it's a ratio of two holomorphic functions. And now the question is, how many zeros and how many zeros can this holomorphic functions have? Well, in the complex plane, yes. Or in the, yes, because otherwise we will have several pre-images for zero or for infinity. So the only option is actually the ratio of two linear functions, az plus b over cz plus d. So that's all. Right? So those are the only functions from compactified C to compactified C. So it is also denoted by CP1. And we can also, it's also easy to see that these functions form a group PGL2 because we can say that they map to coordinates, like to homogeneous coordinates on CP1, Z1, Z2. They map to A, B, C, D, Z1, Z2, and our Z is in the ratio of Z1 over Z2. So the consequence is that it is a group PGL2. And the group of matrices is factorized by scalars. like by multiplication of all these four elements by some number. But so are there any questions about this? But now let us try to play the same game with this disk. Let us look for such a function in the same form. So let us say that that our function is az plus b over cz plus d. And I say that if z is on the unit circle when it is on the boundary, then it should have absolute value 1. So a e to the I phi plus b or c e to the I phi plus d equals to 1. Which means that like a e to the I phi plus b times a bar e to the minus I phi plus b bar equals to c to the I phi plus d c bar e to the minus I phi plus d bar. So we ask for this. We are trying to solve this problem, to find such invertible functions from this unit disk to itself. Yes, for finding such transformation of the whole complex plane. Actually, so let me think. If it is obvious that all such functions should be obtained in this way, yes, it is obvious because we can. No, so is it? No. I can. I cannot say it immediately. Sorry. Or maybe I cannot give a proof that this functions should necessarily have this form. So. No, actually, I can prove that all such functions should be of this form, and this proof looks like this. There is a transformation z goes to 1 over z bar, which keeps the boundary of this circle the same. So. Um, uh, uh, this transformation z to 1 over z bar preserves the boundary. Uh, no, maybe. So is it enough or not? No, I'm a bit stuck. I wanted to use some symmetry argument that if we try to continue this transformation outside the unit circle, we would like to have a statement that it should map this exterior domain also one-to-one. But let me think about this. I forgot how to give a gross proof. But for a moment, let us say that we are just looking for such transformations in this form, and so we have this condition that absolute value of w should be 1 if absolute value of z is 1. So it tells that a bar plus so let us collect all the terms. A bar plus b bar minus c bar minus d bar plus e to the I phi ab bar plus minus c d bar plus e to the minus I phi times a bar b minus c bar d. So and this should equal to 0. And also, if you want this transformation to be invertible, we can ask for something like AB minus CD equals to 1. So we can ask for this for simplicity. All these equations are homogeneous. And so now if you look at this equation, it's actually the same here and there. We see that A divided by C is the same as uh, D bar divided by B bar. Mm. Hmm? Yes. So these two terms uh, mm, are just conjugate to each other. So if we say that this vanishes, then this one also vanishes automatically. Mm. So uh, 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 oh, so it is just the same equation, but complex conjugate of itself. So no, this should also hold. I'm just starting from a solution of that equation. So 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 is it fine? So, actually, I would remember the mass parameterization of all this. Mm, so so we see from here that A equals uh, to some lambda times C, and uh, B equals to uh, uh, to lambda bar inverse. No, so is it fine? So D equals to lambda bar B. Hmm? And no, we just solve this equation. Yeah, but from this one. So, uh, because it should be 0 for any phi. Of course, because so an entire unit circle should map to the unit circle. So we have this equation, and let us also look at this equation. Here we have a lambda, absolute value of lambda squared minus minus 1 times c bar, absolute value of c squared. So it's one term minus lambda squared minus 1 absolute value of d of what of b equals to 0. So from here we can conclude that absolute value of c should equal to absolute value of b. So therefore c equals to some r e to the I phi, b equals to r e to I theta. And now let us look at this last equation, which we asked for determinant to fix overall freedom. So it tells us that lambda minus lambda bar actually not sure if we get something correct after this, but let us go until the end. So let us say that this lambda is some 1/2 r minus 2 e to I minus I phi plus theta. Uh, sorry. Mm, since this since this is a purely imaginary number and this product equals to 1, we conclude that that this exponential is also purely imaginary. So theta equals to pi over 2 minus phi. And so this b equals to pi r e to the minus I phi. So if we do this, then we find that lambda minus lambda bar equals to r minus 2 equals to minus r minus 2. So lambda equals to minus. Hmm? No, but why does it matter? It can have either positive or negative imaginary part. So. Hmm.
So you get different lambda, but anyway you can get all the functions by setting different lambda.
Mm-hmm. So. Mm, but this write some real part for this lambda. And finally, let us. So it seems that we solved all these equations, and now let us write our matrix. So C equals to R e to the I phi. B equals to I R e to the minus I phi. A equals to uh, 1/2 of psi minus I over 2 r minus 2 times r e to the I phi. D equals to
we put plus or minus t in the next step, lambda minus lambda bar equal plus or minus c.
Oh, why plus or minus?
Because we can
Mm.
we just need to have imaginary part, not positive.
Yes, you are right, probably. We should, let me think. Mm.
Put plus or minus e r minus 2 if we choose to maintain the final.
Yes, in principle, yes, we can put different signs here. But sorry. Mm.
Now it's correct.
Yes, we should actually be careful because it is possible to get such transformation which does the inversion of this disk, so it sends interior to exterior, and we should avoid this.
So you want that the pole of the function is outside the disk.
Yes, it's true. So. Um, So we should put here plus or minus, and here minus plus. So B should have plus or minus. Here it's minus or plus. Minus plus.
So one should be minus plus and the other plus.
Yes. Thank you. And here is minus plus. Okay, it's plus minus probably. So it is B. So yes, like this. Actually, I don't. I don't like what we get, but let us transform it a little bit more. So we can notice that. So let us try to write this this B, C, and D as a phase and argument. Namely, let us say that this uh, uh, 1/2 of xi minus plus of I r minus 2 times xi r plus minus r minus 1. It equals to its absolute value, which is classified as 1/4. Mm.
is 1/2, which was square root.
Yeah, 1/2 times pi alpha. Mm. Oh, actually, actually, uh, I actually made a mistake when wrote this expression, I think. Yes or not? Mm. Yes, and now I'm writing something stupid because when I wrote this determinant condition, I wrote that well, I don't know what I written here. So the actual formula is uh, oh, no, maybe it's fine. Uh, so no, the actual formula is since we are expressing everything in terms of Mm, no. Well, I wrote determinant in the wrong way. It is AD minus BC. So I don't know what have I written here. Sorry, it is so the actual formula is BC 1 minus absolute value of lambda squared, and so it equals to 1. And what is written here is complete math. So starting from here, actually. Sorry, there's some stupid mistake. Mm. So if you don't make a mistake in the formula for determinant, then it now tells us that BC, which is r squared e to the I phi plus theta times 1 minus absolute value of lambda squared equals to 1. And now we should ask what is the image of 0. So before solving something, so let us compute W of 0. It equals to A over C. Minus A over no, just A over C. Yes. Sorry. It was no of infinity is V over D. So we should have so and this should be so B over D. So value should be less than 1. And this B over D is uh, mm, is a lambda inverse. So absolute value of lambda should be greater than 1. Mm. So we can say that if it is so, then theta is pi minus phi, and mm, this lambda squared minus 1 equals to r minus 2, which can be rewritten as lambda squared minus r minus 2 equals to 1. And if you want to, well, actually, I still don't like what we get here. Maybe it's fine. Mm. Mm. No, we should write it in a different way. We should multiply it by r squared. Mm. And this can be parameterized in the following way, that r equals to a hyperbolic sine of some psi, and then absolute value of so and then lambda is uh, a hyperbolic sine of psi over hyperbolic sine of psi times e to some alpha. And now let us substitute it to our formulas. So A is so B is now minus parabolic sine of psi e to the minus I phi. C is a parabolic sine of psi e to the I phi. A which equals to, so by this formula, lambda times C is a hyperbolic cosine of psi e to the I phi, and D is by this formula hyperbolic cosine of psi also plus I alpha. here. Parabolic cosine of psi times e to minus I alpha minus I phi. And
Also negative
d,
or the
yes, thank you, that's correct. So finally, our matrix, so ABCD equals to hmm, so, no, actually, there was some sign mistake because we obtained some matrix which has a determinant -1 in terms of 1. And this is because here I made another mistake. I wrote 1 minus lambda squared instead of lambda squared minus 1. So sorry. So if we change it here, then it is -1 here. Lambda is still greater than 1. We should remove this pi from here. And basically remove all these minus signs which were written in these formulas. So, sorry. Yeah, so we obtain such a matrix, and so this matrix looks like a hyperbolic rotation with this hyperbolic cosine and sine, and it also contains some phases. So this matrix ABCD is actually element in the group SU11. And this is the group which preserves preserves a scalar product like x bar minus y y bar. So it like absolute value of x squared minus absolute value of y squared. So so it's called SU is a special unitary, and so I was computing it too long, and so the next time I'm going to use this transformation to finally compute this gain function in the disk. Oh, but uh, But the most important point is that we have such a three-parametric family of transformations, and we can think about it the following way. So there is, of course, a trivial transformation that we can rotate a disk around zero. Then there is so when we then we can perform this transformation and rotate this around some other point which is the image of this zero. This corresponds to this phase rotations. But there is some essential transformation which moves zero to some other point. So. And
This matrix is a both a rotation and also shrink and in some way that the disk rotates itself. So I rotate and also.
so well, maybe we'll draw some pictures on the next lecture. But basically, there are some there are also let me think. So usually, if it takes some trivial transformation, there will be two fixed points on the boundary, and it will move. So and it will. Move this disk kind of from move all these points from one fixed point to another one. But no, what do I want to explain actually? I'm saying some trivial things that we can perform non-trivial transformation which preserves the real line, and we can also perform a rotation before this transformation and after it. So maybe that's all I want to say about it. Okay, so are there any questions? Sorry for these mistakes in the computation. I thought that it will be easy, but no.
So SU11 is the group of two matrices that when we compute the matrix times its conjugate transpose, we get 1 minus 1.
Yes, the matrix is not a sum of absolute values squares, but with minus 1.
Is orthogonal with respect to this scalar product.
It's a unitary in a sense that this scalar product is it's called half linear, that like lambda u mu v equals to lambda bar mu u v. So it is this half linear scalar product with 1 minus 1 signature, and it is preserved by such matrix. And we will also see that this group is actually isomorphic to SO2R. But we will also see why it happens. Okay, so transfer attention.